Welcome students. Today we are going to discuss about exact differential equations and integrating factors. So before we go on exact differential equation, let me quickly go through the partial derivatives. So consider your function phi xy, which is a function of x and y both. So it has two independent variables in, which are x and y. Now you can consider partial derivative of phi with respect to x. In this case, you will treat y as a constant. So partial derivative of this with respect to x. So derivative of x square is going to be 2x. Now y square is a constant with respect to x. Y is a constant with respect to x. So you have derivative of y square is 0. And derivative of 2xy, y is a constant, 2 is a constant. So 2y is a constant, comes out times derivative of x, which is 1. So this is partial derivative of phi with respect to x. Similarly, we can talk about partial derivative of p with respect to y. In this case, x will be considered as constant. So you have first part is 0, then derivative of y square with respect to y is 2y. And similar to the previous one, here 2x is a constant which will come out, and derivative of y is 1. So these are the partial derivatives. Now, what is an exact equation? So you again start with a first order differential equation. So a first order differential equation given by mxy plus nxy times dy by dx equals to 0. So this differential equation is exact if you take partial derivative of m with respect to y, and that becomes equal to partial derivative of n with respect to x. So such a differential equation is exact. And such differential equations, for such differential equations, there is a technique to solve differential equation. So which we'll see as below. So now, solution to any exact partial differential equation like this, sorry, my bad, any exact differential equation like this is given by phi of xy equals to c. So this is an implicit solution where c is an arbitrary constant and phi satisfies dou phi by dou x is m, and partial derivative of phi with respect to y is n. So let's see why that holds. So suppose phi of xy equals to c is a solution. Now differentiate both sides with respect to x. Now note that in this case, when you write phi of xy equals to c, y becomes automatically a function of x. Yeah, because y is no longer independent of x, right? So we'll differentiate both sides with respect to x. So what do we get? So we'll have to use chain rule. So we get partial derivative of phi with respect to x times dx by dx plus partial derivative of y with respect to, sorry, partial derivative of phi with respect to y times d phi by dx equals to 0. So that is, we get, so this can be thought of as your m. So this is 1, right? So mxy plus this can be thought of as n, this can be thought of as m. So you get n xy dy by dx equals to 0. So it satisfies the so this is how the this is how the exact differential equations work. Now, let's look at the following problem. So find an implicit expression for a general solution of the differential equation 2xy plus x squared plus y squared dy by dx equals to 0. So first, we show that this differential equation is exact. So let's call this as m. Let's call this as n according to the convention. Okay. So we a priori do not know that this differential equation is exact. If this differential equation is not exact, then we cannot at the moment find such a phi. We'll have to, at least not straight away, we'll have to do then maybe something else. So first, show that this differential equation is exact. So compute partial derivative of m with respect to y and check if it is equal to partial derivative of n with respect to x. So if you look at m, which is 2xy, if you take partial derivative of that with respect to y, 2x is a constant, comes out, partial derivative of y with respect to y is 1. So we get 2x. Similarly, partial derivative of n with respect to x is going to be, the first one will be 2x and the second one will be, y square will be 0. So therefore we get, since this is equal to this equation is exact. Is exact. Yeah. So what does it mean? It means that there is a solution phi. So this means there is, so this means that there is a solution of form phi of xy equals to c. Now the question is, how do you find such a phi function? So note that if you look here, your m is partial derivative of phi with respect to x. So our m is, so we want to find phi, function phi, we have by y. So if you look at partial derivative of phi with respect to x is going to be m, which is 2xy, and partial derivative of phi with respect to what, with respect to y is going to be n, which is same as x squared plus y squared. So now we want to integrate one of them. Let's make a choice. So let's choose this one. So integrate this guy here first. So phi of xy is going to be integral of partial derivative of phi with respect to x dx. That is going to be 2xy dx. Now y the constant comes out. Integral of 2x is going to be x squared. Now note that you're taking partial derivative with respect to x. So there will be constant, but the constant can depend on y. So we have h of y. Why is that? I mean, if you look at of this guy here, this is going to be 2xy plus 0. So that means integral of this with respect to x. So integral of this with respect to x is going to be x squared plus hy. Now, where h of y is a arbitrary function to be determined, function of y variable and only y variable. So now we have gotten phi of xy equals to x squared y plus h of y. Now we need to find out what is this h of y. So how do we go about it? So what we'll do is we'll take derivative of phi with respect to y and then equate it with n, because after all n is partial derivative of phi with respect to y, right? So let's do the derivative of phi with respect to y. On one hand, when you take derivative here, you will see that this is going to be x squared plus h prime or h of y. This means it's a derivative of y with respect to derivative of h with respect to y. Now on one hand we get this, on other hand this is equal to, from here you can see that this is equal to x squared plus y squared. Let's call this a star, and then we can say from star. So this would mean hy of y equals to y square after equating this. So this would mean now everything is happening with respect to y only. This would mean h of y is what? Integral of this with respect to y only, which is going to be y cubed by 3. So therefore we get phi of xy equals to x squared. So from here you can see that phi of xy is going to be x squared y plus, instead of h of y I have y cubed by 3 equals to c. So this is your solution. Now you may say, well, you integrated here with respect to dy, and why didn't you write a constant? Because you're doing an indefinite integral. Well, as long as you write it equal to c, you can absorb that constant in the c. Okay. So this can be mentioned here in the remark. When we integrate h prime y equals to y square, or h of y with respect to y, derivative of this equals to y squared, we do not need to choose arbitrary constant, since phi of xy already involves an arbitrary constant. Okay. Now suppose if at any stage, if you equate partial derivative of phi with respect to y and that with respect to n of x, and the terms in variable x do not cancel out, that means if you equate and you do not get h of y, that means you have done something incorrect. So typically either the d was not exact to start with, or you have made some algebraic mistake along the way. Now note that there was no reason why we chose to start with what? Integrating m dx, right? So you can see this is integration of really m dx. Yeah, you could have started with integrating n with respect to y as well. Okay, and then apply this rule. So this will lead to exactly the same function. So the algorithmics is pretty straightforward. What you have to do is first you have to check if the equation is exact, and if the equation is exact, then you have to employ the technique mentioned in part C. So let's see. So here, if you compare it with mxy plus n xy dy by dx equals to 0, we see that m is going to be 1 plus ln x plus 2x ln y, and n equals to x squared by y minus 2y. So first thing to check is whether this equation is exact or not. Okay, so let's see. So let's compute partial derivative of m with respect to y, and then partial derivative of n with respect to x, and check if they are equal. So what is the partial derivative of m with respect to y? So 1 is a constant, will be 0. Ln x with respect to y is also 0. 2x is a constant, comes out. Derivative of ln y is 1 over y. So I can write it as divided by y. Here partial derivative with respect to x. So 1 by y is a constant in the first part, and derivative of x squared is 2x, and minus 2y, derivative with respect to x is 0. So you can clearly see that partial derivative of m with respect to y is equal to partial derivative of n with respect to x. So since these are equal, the equation, the differential equation is exact. And since it's exact, there is a easy way of finding it. So you start with what? You start with equating. So we know, so this implies there exists phi of xy equals to c, a solution to given DE, differential equation. So now I'll start. So I will say this is equal to mxy, which is 1 plus ln x plus 2x ln y. So I'm going to integrate this with respect to x. So I get integrating with respect to x with respect to x, we get phi of xy equals to integral of 1 plus ln x plus 2x ln y dx. Now this is going to be integration of 1 with respect to x is x. Now integration of ln x has to be done by parts. So you will see that is equal to ln x minus x, and integration of this with respect to x. So ln y is a constant, so you get x squared ln y, and then plus a h of y. Or in other words, we have phi of xy is equal to x ln x, because these x will cancel out each other, plus x squared ln y plus h of y. Now we have gotten phi. Now we need to determine what h of y is as a function. So for that, we'll do the following. The second step is to take partial derivative of phi with respect to y and equate it to n. Find this guy and equate it to n. So we get what? If we do that, we have partial derivative. So we have this with respect to y of x ln x plus x square ln y plus h of y is going to be, so this is going to be 0 because there's no y in it. So 0 plus x squared by y plus h prime y. Now I'm using a different notation here. By h prime y, I mean the same thing. Derivative of y with respect to y. So if we equate this, this is equal to, however, what? This is equal to, if you go n is x squared by y minus 2y. So let me call this a star. And this is equal to x squared by y minus 2y, yeah, from star. So what do I get when I equate this? I get h prime of y equals to minus 2y. This would give me h of y is integral of minus 2y dy, which is going to be minus y square. And again, I'm not adding a constant because that constant will be observed when I write phi of xy equals to c. So therefore, the solution is phi of xy equals to x ln x plus x square ln y. So this part, and then instead of h of y, I have simply y square. This equals to constant c. So this is a solution. Yeah. So now comes the point of integration of ln x dx. So just to recall, how did you integrate ln x dx? So recall, you had, if you take ln x dx, you can use integration by parts. So your u is ln x and your dv is dx. And recall, integration of u dv is uv minus v du. So what is your v? Your v is integration of dx, which is x. And your u du is 1 over x dx. So uv is going to be u ln x. V is x minus v du, which is going to be x, times du, which is 1 by x dx. So this is going to be ln x times x. These x will cancel off, and integration of dx is simply x. So minus x plus a constant c. So this is how it works out. So that's why here we have replaced directly what? Integration of ln x in this part. Integration of ln x was replaced as ln x minus x. So x ln x minus x. So x ln x minus x. All right, again. So let's recall what our goal is in this. We are trying to solve a first order differential equation given a form m of xy plus nxy dy by dx equals to 0. Now suppose if it is not exact, then what do we do? Now, if it is not exact, sometimes it is possible to find a function mu of xy, which you multiply throughout and the equation becomes exact. Yeah. This, in general, this mu of xy may be difficult to find, but in some cases it's very easy to find mu of xy. So we'll focus mostly on those cases. Yeah. Note that these kind of differential equation we have now, we have been developing tools for this, right? So we have developed what kind of tools? We have, for first order differential equations, we have developed the tool of separable differential equation, we have developed the tool of how to integrate this, the first order linear differential equation. Yeah, there are special cases here. So now let's deal with the case when you have mxy plus nx dy by dx equals to 0. Suppose it's not exact and we multiply by mu xy throughout. Well, if you multiply 0 with mu xy, you'll get 0 and it becomes exact. So let's see what such mu of xy is. Now, such a mu of xy is called integrating factor. You should make the connection with the first order linear differential equation to see why it is called integrating factors. So now in general, if your mu is a function just of x only or y only, it is easy to set up this whole thing. So let's see. So suppose my mu, I multiply by mu x throughout, xy plus mu x and xy dy by dx equals to 0 is exact. So what is the idea? You start with an equation which is not exact. So start with something which is not exact. That means what? Partial derivative of this guy with respect to y is not equal to partial derivative of this with respect to x. That is what it means by not exact. So we multiply by mu x throughout, hoping that will make it exact. So let's see, what does it mean by it being exact? It means by saying that this nu is exact is same as saying this, let's call this as m bar, let's call this as n bar. So if this is exact, this differential equation is exact, we need what? We need partial derivative of m bar with respect to y to be equal to partial derivative of n bar with respect to x. Yeah? I mean, we're calling this new function as n bar, new function as n bar. Okay. So this would mean what? So first, let's take partial derivative of m bar with respect to y. Here, mu is a constant, so with respect to y, so it will come out. You will simply have my. This is another short notation for partial derivative of m with respect to y can be called as my. And on the other hand, if this is equal to partial derivative of n with respect to x, then what should happen? Now here we'll have to employ the product rule. So we have first mu prime x times nxy as it is, plus what? Plus mu x times nx. Again, what does this symbol means? The symbol is simply nx. Yeah, there's a small subscript there. So now this means that these two things are equal. So therefore, what do I get from here? So what should my mu satisfy? So bring this guy on the other side. So I have mu of x my minus mu of x nx equals to mu prime x n of xy, or you get mu prime equals to m. So I'm going to basically take this guy and divide it by on the other side. So I get what? I'll get mu prime equals to my minus nx. I take mu x common from here and divide by what? Divide by n of xy. So this means that, so this side is a function of what? Function of x only. Now this side is a function of x only, right? Because mu is a function of x, so mu prime and this guy, so these are function of x only. So this means that this must be function of only x in order to have uh, this system work. What system work? That there is an integrating factor of form mu x. Now the same argument can be repeated with some function of y as well. Yeah. So this is a necessary condition. Necessary condition to be able to find an integrating factor of form mu x. So let's look at the following problem. Find an integrating factor mu equals to mu x to make the following differential equation exact. So here again, we have this part is your m and this part is your n. So let's see, first of all, is this differential equation exact? So we have m y, that means partial derivative of this with respect to y is going to be, what is derivative of this with respect to y is going to be y squared, and partial derivative of n with respect to x is going to be what? Derivative of y squared with respect to x is 0. So we have what? Since my is not equal to nx, the dE, the differential equation, is not exact. So now let's check whether we can find an integrating factor of the following form. So let's compute my minus nx divided by n. So what is my minus nx divided by n? We get what? We get that is equal to my is y square, nx is 0 divided by n, which is y square. In this case, we'll get this is equal to 1. So this is a function of x, right? I mean, it's a function of y too. And this is a function of x, most importantly, and is independent of y. Yeah, we don't want any y there, right? So now how do we go about it? So what do we need? We have mu x, so we get mu prime. So we get what do we have? We have mu prime equals to my minus nx over n times mu. So this means mu prime equals to what? 1 times mu. And you know, this means mu x equals to e to the power x, right? I mean, why is that the case? This would imply mu prime by mu equals to 1. And then, you know, this happens if you integrate on both sides, you'll see that the answer is mu x equals to e to the power x. So now, so when you multiply throughout by e to the x, this equation becomes exact. So e to the x times the original differential equation, which was 1 by y, 1 by 3 y squared plus e to the power minus x, the whole differential equation. So y squared dy by dx equals to 0 is exact. Now is exact. Okay. You don't need to check that because that's how you constructed your mu. So in this case, you have now your new m is going to be multiply this inside. So we get 1 by 3. Hold on. So this is 1 by 3 y cubed, not y squared. So 1 by 3 y cubed e to the power x plus e to the power x times e to the power x is 1. And n equals to, when you multiply it with this guy, you get e to the power x y square. Yeah. So now we have, this is our m and this is our rather new m and new n. Now this is exact. That means what? So this d is exact. You may want to check it again. However, from the way we have constructed it, there is no reason to check it because, you know, we constructed mu based on our earlier theory here. Okay. However, it's a good idea to just check it and see what is happening. So now what do we have? That means your phi function, derivative of that with respect to x is 1 by 3 y cubed e to the x plus 1. And your derivative of phi function, what is your phi function? Phi is the solution, right, to this differential equation. So we are trying to extract phi out of it now. So now what do? You can proceed now as usual. Let's just finish this problem. So what do I get? I get phi of xy equals to integral of phi with respect to x dx, which is going to be 1, integration of this with respect to x is going to be 1 by 3 y cube is a constant, e to the x integral is e to the x, integration of 1 is x plus sum h of y as a function. So let's call this as star, let's call this as hash. Now differentiating equation hash with respect to y, we get y equals to y square e to the x plus 0 plus h prime y. Now if you equate these two from there, you get h prime y is 0. This means h of y equals to some constant k. Right? Therefore, phi of xy equals to, what do we get? E to the x y cubed by 3 plus x equals to c. I'll bring that k in the other constant c is a solution to above DE, which was not exact, but you made exact. So now we have few more tools in hand, and that's about it. Thank you for your attention.